Welcome everyone. This is the monthly journal meeting for the Tucson Amateur Astronomy Association, and we're very glad to have you here. We typically meet both on Zoom and in person and Facebook. Um, we tonight, however, are not meeting in person due to some room scheduling issues, but we will be back next month to holding our meeting both, online and in person. So we're just glad that you're all here. I'm May Smith. I'm TAAA president. And tonight we have Terry Lappin, who is doing all of our technology work for us tonight. We often have 2 or 3 people working on technology, but Terry ended up to be our sole person tonight. So we have a superwoman running everything tonight for us, and everything will go very well, I'm quite sure. So we're so glad that you're here. We have one guest speaker tonight, and her name is Dr. Adine Denton, and I'm sure you received some information on her, and she's going to share some very information with us on Pluto. So, Dr. Denton?
All right, I'll take it away. One moment. All right, here we go. Thank you so much for having me. And also, if there are any sound issues, just let me know. I am so happy to be with you all today. I am a planetary scientist specializing in the study of outer solar system objects. In particular, I really like to study Pluto. So what I'm going to discuss with you tonight is a bit about some recent improvements that we've made into understanding Pluto's history and how it evolved over the course of the solar system. So that's why this is called Pluto's past and Pluto's present. So I'll begin with a little bit of history about our understanding of Pluto and our exploration of Pluto. So prior to the New Horizons flyby of Pluto in 2015, we didn't understand very much about Pluto because it's simply so far away that it's very difficult to observe. This is a composite image taken by the Hubble Space Telescope, which revealed that Pluto is a rotating blob with some light areas and some dark areas. So when New Horizons launched in 2006, this is really all we knew. And we targeted Pluto as best we could to get some more answers. The surface of Pluto that emerged following the New Horizons flyby turned out to be even more interesting than we anticipated because it's so geologically complex. I am a planetary geologist by training, so what I find most interesting about Pluto is the fact that it seems to have a relatively widespread geologic history. It's covered in extensive superficial geologic activity, including mountains that are made of water ice and glaciers that are made out of volatile carbon monoxide, carbon dioxide, and methane ices. And it's covered in these globe-spanning troughs and scarps, like this one that I've highlighted here. This is called Virgil Fosse, after the poet. And of course, the surface is dominated by the elliptical basin known as Sputnik Planitia, which is sometimes called Pluto's heart. If you've seen Pluto in the news, it's because they're talking about Pluto's heart. And I've highlighted it in red here at the center of this image. There's a lot of really interesting things about Sputnik Planitia. First, because of its large size, its elliptical shape, and its low topographic signature. That is the fact that it's a giant hole in the ground. Scientists have suggested since it was first observed in New Horizons imagery that it is a massive impact basin, because there's not a lot of good ways to get a massive hole in the ground anywhere in the solar system, but one way to do it is to hit something else very, very hard. And the interesting thing about Sputnik Planitia is its size, shape, and its current location, literally where it's located on Pluto, has been used as evidence to suggest that Pluto has a subsurface ocean. And that's something that I'm going to talk about in a lot more detail in this talk, because the ties between this geologic feature and Pluto's interior can be critical. But the global influence that the formation of Sputnik Planitia had on Pluto remains largely unknown. It was probably quite traumatic for Pluto to make a hole this big. Sputnik Planitia is larger than the state of Alaska in terms of surface area. So it probably had some sort of global ramifications, but we don't fully understand the details. And before I talk more about Sputnik Planitia, I want to talk a little bit about Pluto's interior and what we know and don't know. And this is as up to date as I can make it in terms of what we think about Pluto today. So I'm going to start from the bottommost part of Pluto, so the bottom part of this little pie slice, and work my way to the top. So that means I'm going to start with Pluto's core. Pluto, like the Earth, has core. And we're pretty sure that that core is made of rock based on Pluto's total average density. But the size of Pluto's rocky core is mostly known, but the composition of that rock is something that we don't fully understand. We know its size based on evidence of, again, Pluto's total density and its size, and the assumption that it differentiated, meaning that it's separated fully into an outer crust made of ice and potentially water, and then an inner core made of entirely rock. It's been suggested that Pluto's core could have undergone hydrothermal alteration, which means, so it's similar to what's happening on the ocean floor at those deep sea hydrothermal vents, that the water on top of Pluto's core and the core itself are chemically interacting, which could release elements that are useful for the development of life, which is why we care. But that's not something that we can really tell just by looking at Pluto's from the surface, which is all we really have from New Horizons data. So there's a lot we don't know about the core. Moving up, we get to an interesting question, which is, does Pluto have an ocean today? And did it have one in the past? And that's actually a pretty interesting question because we're not quite sure. There are several lines of evidence that suggest that Pluto might have a subsurface ocean. And by subsurface ocean, what I mean is that Pluto's surface layer is a water ice shell that acts as Pluto's crust, similar to the Earth. But underneath that crust, there might be a potential liquid layer, which would then be a global liquid water ocean. There's a couple points of evidence that indicate that that's possible. The first being what we call extensional tectonics. These are the lines that I've mapped out in the different colors in this image, which are green, yellow, and red. These point to extensional tectonics on Pluto. What that means is that we think that Pluto expanded at some point in the past, and that that expansion slowly pulled the planet apart just a little bit. The reason that's evidence for an ocean is because water is less dense than ice. But if an ocean forms and then gradually starts to freeze as Pluto cools off over time, similar to how the Earth is cooling off today, then that ocean will slowly start to freeze and turn to ice. And because water expands when it turns into ice, the entire planet expands, forming these extensional cracks. The other point of evidence that I want to talk about is literally the location of Sputnik Planitia itself. And this point of evidence is a little bit more contentious and potentially a little bit more confusing. But if we take a look at where Sputnik Planitia is on this image relative to Pluto's equator, which I've indicated in this red arrow here, this is the Pluto-Charon tidal axis, but it, for all intents and purposes, is Pluto's equator. Sputnik Planitia is really, really close to Pluto's equator. It's within 10% of it. And that's unusual. It shouldn't really be there. And the reason it shouldn't really be there goes into how planets distribute their mass. Sputnik Planitia is theoretically an impact basin, which means it's a topographic low. We know this from topographic data from New Horizons. But if Sputnik Planitia is indeed a mass negative, where you literally remove mass to make the hole in the ground, planetary dynamics suggests that if you want to minimize your energy state and your missing mass, the missing mass always rotates up to the poles. Similarly, the converse is true. If you have a point on a planetary body that has too much mass, that will preferentially tip towards the equator for the exact same reason. It's the lowest energy state for the planet. So because Sputnik Planitia is so close to the equator, it's led people to suggest that it's what we call a positive mass anomaly, where Sputnik Planitia actually has too much mass rather than too little, and it's reoriented Pluto to place Sputnik Planitia where it's currently located, similar to how the Tharsis volcanic complex on Mars is close to the Martian equator. And how would you do that? How would you have too much mass rather than too little? Well, one of the things that contributes to that is the white that's filling Pluto to Sputnik Planitia today. The white of Sputnik Planitia is actually nitrogen ice that forms the heart, and nitrogen ice is more dense than water, so that adds some mass, but not enough. The other component, then, we think, is that the ocean has literally been uplifted beneath Pluto's heart. That if we were to drill down through the center of the heart, we would reach the ocean a lot faster than we would anywhere else, because when the impact itself formed Sputnik Planitia, it thinned the ice under the basin and pushed the ocean up to contribute extra mass. So that's a point of evidence in favor of having an ocean, but it's a little bit circumstantial. So we think there might be an ocean, but we don't know for sure. Lastly, Pluto's ice shell. That's what we see on the surface, so we know the most about it. We know that it's largely water ice with a thin veneer of surface volatiles. And by volatiles, I mean the more exotic ices that you don't see around here, but which solidify on the surface of Pluto, because the surface of Pluto is 44 Kelvin, which is more than -300 degrees Fahrenheit, I think. Those are nitrogen ice, carbon monoxide ice, and methane ices, those kinds of things. And those are best exemplified by the 3 to 10 kilometers of nitrogen ice that are currently filling Sputnik Planitia today. But when it comes to trying to understand what this shell around Pluto even is, beyond knowing its composition, we're not really sure how it works. We don't know we know how warm it is at the surface, which is not at all, but we don't know how warm it is at the base. And if there is an ocean, we don't know how thick the ocean is relative to the ice shell. People have suggested that if you have an uplifted ocean underneath Sputnik Planitia today, then that means that the ice shell has to be relatively cold and stiff, because otherwise, if it was warmer, the ice would tend to flow, just like glaciers do on Earth. And if the ice tends to flow, then it refills the hole, which, in addition to filling the hole of Sputnik Planitia, also fills the hole under the ice shell, removing the ocean. So if we believe that Sputnik Planitia is an impact basin with ocean underneath it, then the ice shell needs to be cold and stiff. But we don't know how that really works, how thick the ice shell might be, and what thermal structures are possible within that kind of framework. So just to recap, here are the major unknowns in Pluto's interior. The first is, does Pluto have an ocean? The evidence is there, but it's largely circumstantial. Second, Pluto's core. Has Pluto's core undergone some form of hydrothermal alteration in the past? And if it did, then could Pluto potentially be a more suitable place for life? It's not as outrageous of a question as you might think. And then lastly, how thick is Pluto's ice shell really, and how is it structured? These are all pretty big questions, but the good thing is they're also all testable parameters that we can investigate by doing some science. So let's talk a little bit about the science that we're going to be doing. The big motivating question behind this work is, what is Pluto's thermal and mechanical structure, and how has it evolved over time? Meaning, how hot has Pluto been in the past, and how is that reflected in Sputnik Planitia? And then mechanically, how much of Pluto is ice and how much of it is water? Those are all things that we can try to figure out. And we can do that by using Sputnik Planitia to take a look inside the planet. The reason that we can do that is because of the unique properties of large impact basins. When a massive asteroid hits a planet, several very special things happen in terms of the physics. And in particular, it leaves a very specific signature behind, which means that the presence, persistence, and morphology of Sputnik Planitia, everything about how it looks today, directly reflects Pluto's thermal and mechanical structure at the time that the basin formed, which leads us to the hypothesis that guides some of the work that I've been doing over the last couple of years, which is that we can use giant impacts to inform our understanding of both thermal and mechanical variations in Pluto's interior, that we can use this process to get at some of these fundamental questions. So some of those questions are: how hot is Pluto's ice shell in its ocean? How much of Pluto's interior is solid ice versus liquid water? And has Pluto's core changed in composition over time? So the primary goal here then is to literally use the formation of this basin to inform our understanding of these variations, both in terms of Pluto's short-term and long-term evolution and how the basin evolves with it. So the first thing I'm going to do is look what happens in the first 1,000 seconds after the impact forms. And then the second thing I'm going to do is explore Sputnik's evolution over geologic time. We might not have time to get to that. And if we don't, you can absolutely ask me about it later. So first, let's talk about what happens when Pluto experiences a massive giant impact in those first 1,000 seconds after impact. So why do we want to know about this at all? Well, here I've plotted a map of Pluto, similar to how a map of the Earth would be plotted, but I've centered it on Pluto's far side, which is the hemisphere that we didn't get such a good look at. So Sputnik Planitia, which was in the center of all the previous images, is now at the edges, and I've highlighted it here in red. Now, if we take a look at what's in the center of this image on Pluto's far side, you may observe this region of disrupted and lineated terrain that I've highlighted here. What's interesting about this terrain is that it's roughly antipodal to Sputnik Planitia. And when I say antipodal, what I mean is if I were to start at the center of Sputnik Planitia, drill down through the planet, through the core, and out the other side, this terrain is what would be on the other side. They're directly across from each other on a planetary scale. And it might be kind of weird for me to suggest that these are somehow related, but it's actually not out of the question, because these so-called antipodal terrains are something that have been observed in association with other large impacts across the solar system. So what I'm showing you here are two similarly large impact basins. The left is Imbrium on the moon and the right is Caloris on Mercury. These are both huge. And if we look at their antipodes, go to the other side of the planet and see what's there, what we observe are these hilly and lineated surface features that are formed in association with seismic shaking from seismic waves that are released from the impact. So we're going to do a little bit of astronomical seismology tonight. Basically, here's what happens. Think about an earthquake. An earthquake is kind of like a point source released inside the Earth. When an asteroid hits a planet and the impact occurs, that impact acts as a similar point source that releases seismic waves that expand through the planet. If the impact is large enough, like the one that formed Sputnik Planitia, then as those seismic waves expand, they don't decay like a normal seismic wave would on the Earth. That's why we don't get earthquakes that span the globe. But on Pluto, those seismic waves remain powerful enough that they're focused by planetary geometry and then converge at Pluto's antipode. It's similar to how light gets focused to the back of your eye. And the cool thing about this phenomenon is the magnitude and extent of any deformation that occurs at the antipode to a large impact is highly dependent on the internal structure of the target body, which means we can use this. So the key question here is, can we use the formation of Sputnik Planitia's antipodal terrain to constrain the internal structure of Pluto? And from there, what can we learn? So how I'm going to do this is I'm going to, on the computer, build a bunch of different Plutos, an army of Plutos, with varying internal structures. And then I'm going to simulate the Sputnik Planitia forming impact into those test planets and watch what happens at the antipode. And those simulations look a lot like this. They do not. We do not have the technology to actually blow up Pluto in detail at this time. But I still want to talk to you a little bit about how the models work and how science actually gets done, because it's still really, really cool and interesting, but it's also a lot simpler because of the limitations of what we can do. So what I'm showing you here on the left is the Pluto that I can build in a computer and then hit with a large asteroid. And here I'm simulating Pluto as basically 3 layers. So Pluto has a rocky core, and then it has an ocean, and then it has an ice shell on the top, and that's all. I'm applying what's called a central gravity field, which basically means I assume that Pluto is a perfect sphere and that gravity increases radially with distance from the center of the planet. It's not a perfect sphere, but in all honesty, this is good enough. And then I simulate the entirety of Pluto at 2 kilometers spatial resolution, and then I hit it with a large impactor that's traveling at 2 kilometers per second, which is the average speed of stuff traveling around in the Kuiper Belt, we think. There's a couple additional things I have to do. I have to decide how big my impactor is, and in this case,
Dr. Dent, can I interrupt?
Yes, go ahead.
Your sound dropped down, and so people are having a little bit difficult time hearing you. Don't know what happened, but just in the last minute, I guess.
Interesting. I can.
A little better.
I'll mute and unmute myself.
Okay.
Do I sound any better?
Yes.
Great, fixed it. No problem. Okay, so let's keep going. Let's talk a little bit about what I'm testing. So I'm testing 2 different things about Pluto that I think might dictate antipodal deformation. The first is, again, whether Pluto has an ocean or not. And I test ocean thicknesses between no ocean at all, so just ice over rock, to a relatively thick ocean. That's about half the total size of Pluto's ice/water component. And then I also test the composition of Pluto's core, whether Pluto's core would be dry and not have had any kind of hydrothermal interactions at all, and whether it's wet and has had some form of hydrothermal interactions. So those are the 2 main things that I'm looking at. And now I'm going to walk us through some of my successful results, beginning with this GIF of my best fit case. So the colors that you're looking at here are tracking the velocity of the seismic waves that are traveling through Pluto. And at the top of this image, that's the formation of Sputnik Planitia. So that's the basin opening at the top. And if you look at the bottom of the image, that is the antipode. So that's what we're interested in. And what we really want to focus on is what's going on in between those 2 points. So that's the passage of the seismic wave right there in the yellow, and that's it reaching the antipode. Now, that's probably quite confusing, and I've also been told quite hypnotizing. So I'm actually going to pull this out into a time series so that we can look at what's going on in more detail. And one other thing that I'll note here is that this is the best fit case. And what we found works the best is if Pluto has a wet core that's had some hydrothermal alteration and it has a thick ocean. And I'm going to talk a little bit about why that is, but keep that in mind as we look at what's going on here. So if I look at this first time step, that right there is the expansion of the stress wave. You may have learned about P and S waves in any earth science class that you took. These are the P and the S wave traveling through Pluto's core. And one thing to note is that that's the wave in Pluto's core, but this is the wave in Pluto's ice shell, which is traveling a little bit slower because 2 reasons. One is the sound speed of rock and ice is very different, as we'll see later. But then the second is that they're separated by this liquid water ocean. So eventually the core arrives at the antipode, but it's followed by the wave in the ice shell, which is delayed. The wave in the ice shell eventually arrives at the antipode, producing the second high velocity pulse. And all told, this takes about 1100 seconds. Now you might be asking, okay, so we definitely focused a seismic wave to the antipode, but what really happened? What actually happened at the antipode? Well, I can tell you, but to tell you, I'm going to have to show you some absolutely terrible plots. So what I'm showing here is strain experienced in the ice shell at the antipode. Strain, for those of you who don't know, is literally the change in size of something. So it measures whether something's getting extended or pulled apart or compressed, which is pushed together, because both of those things would change something's size and shape. So I'm trying to look at whether the ice shell is getting pulled apart or pushed together. So positive strain would be extension and negative strain would be compression. And I'm trying to see if we get a huge zone of strain in the region surrounding the antipode, which is what I've highlighted in those brackets. That would be the total radius. And the interesting thing about what we found is here I'm showing the simplest case we tested, which is just ice overlying rock. So there's no ocean here. And what we found is that we formed this zone of extensional strain, which means the ice is getting pulled apart and we should form something like a canyon potentially in this region. But what's interesting is if you change the presence and thickness of an ocean, this peak starts to change. Specifically, what happens is if I add a thin ocean at the base of the ice shell, we no longer have any extensional zone. Everything is basically close to zero. And the reason for this is actually pretty straightforward if we think about it. Pluto's ice shell is now insulated from the core by this liquid water ocean. And the liquid effectively acts as a buffer because it's much lower in sound speed than the ice above it. That's why I'm showing the sound speeds on the lower left. So basically what happens is as the wave traveling through the core hits the barrier between the core and the ocean, more energy gets reflected back into the core instead of transmitted to the antipode. So the ocean effectively damps out the seismic waves that are traveling through Pluto. But that's actually not entirely the case, because what we found is that as we gradually increase the thickness of the ocean, we get more and more extension. But then suddenly we found if the ocean is very thick, which is what I'm showing you here in pink, we get this massive spike in strain. And the reason for this is because of a corollary effect that also happens when the ice shell is really thin. So the dampening effect that the ocean has on seismic waves that are passing through the core is still true. But now the ice shell is really thin. And when the ice shell is really thin, all of the seismic energy is concentrated into a relatively small area and preserved to the antipode. Similar to, it's basically a waveguide effect, similar to, if you're familiar with waveguides from engineering, it's a very similar phenomenon. Basically, the ocean is trapped, much like the ocean traps waves traveling through the core, it also traps waves in the ice shell. So energy gets preserved and enhanced at the antipode. Now, the other factor here is core composition. And what we found is, so here I'm showing two different core compositions. So the dry core is in white and the wet core is in cyan. And what we found is a wet core, which has a lower sound speed, tends to have better energy transmission from one side of the planet to the other. And that's because there's less of a contrast with the overlying ice shell. So more energy gets transmitted in a wet core than a dry core. And that's true for all ocean thicknesses, but particularly true when the ocean is very thick, because then you also have the waveguide effect from the thin ice shell. So what this means is what we need to make the most amount of deformation on Pluto at the antipode to Sputnik Planitia is both a thick ocean and a wet or a serpentine core, which is very interesting. It's quite possibly the most interesting result. But you might be thinking, this is just a lot of squiggles. What's actually going on at the antipode? Well, we can make some basic estimations of what's going on. If you remember that these strains are extensional, which means, again, the ice shell is getting pulled apart. And extensional strains suggest the formation of large graben or canyons. So you pull the ice apart and you form two normal faults, drop down the ice in the middle, and you form a canyon. And we can predict the depth of those features based on the amount of strain that gets distributed over this area. And what we think is that these canyons should be between 2 to 3 kilometers deep, which would put it at deeper than the Grand Canyon, but similar to the depth of features on the near side, like Virgil Fossé, which is what I'm showing you here on the right. So if we were to return to Pluto with a Pluto orbiter and got better images of these far side lineations, they might be similar to what we've seen on the near side, and I hope we do. But the key takeaway here is that with an ocean and widespread water-rock interactions, which we both need in order to make this work, Pluto could potentially be a much more habitable environment than previously anticipated, which is pretty fun. Now, the second thing I want to talk about here is how Sputnik Planitia evolves over geologic time. Because there's a lot more that happens when an impact basin forms beyond just what's going on as seismic waves travel from one end of the planet to the other. There's also the formation of the impact basin. So I'm going to zoom in space to take a look at that in more detail. And the first thing I want to talk about is the basin's size. So this is Sputnik Planitia. The initial estimates of the basin were kind of an underestimate of how big it was. Our second crack at it accidentally assumed that the basin's a little bit too big. So our most up-to-date estimates of the basin place it at somewhere in the middle, which is 1,200 by 1,400 kilometers. And again, that's around the size of the state of Alaska. And understanding how big the basin is really important when we try to model it, because the size of the basin will affect how it interacts with Pluto's interior. Now, so what I'm going to talk about here is literally which thermal and mechanical conditions produce basins that are consistent with Sputnik Planitia. We're going to try to model the basin in much more detail and see if we can get something that's as close to what we've observed from New Horizons as possible. So how are we going to do that? Well, I'm going to bring in the influence of temperature. The models are going to essentially be similar to what I showed you in the previous slide, but now as I'm showing in this figure, I'm thinking a little bit more about how warm Pluto's ice shell is as well. So again, I'm simulating Pluto in 3 layers. That outer layer is going to be water ice, then a liquid water ocean, and then a rocky core. Everything else is the same. I've had to change a couple things, but the main thing I'm thinking about is how Pluto's evolution dictates how it responds to a massive stressor like a huge impact. And in particular, we don't know how Pluto initially formed. Pluto could have formed really cold, or it could have formed relatively warm. And that's something that's really hard to place limits on. So that's why I've tested basically 4 end member hypotheses for how Pluto may have looked when an asteroid hit Pluto in the distant past. Either Pluto had a really, really thin ice shell, or it had a relatively thick ice shell, and within those 2 possibilities, Pluto was either relatively warm or relatively cold. And I'm happy to explain later why relatively warm is still this cold. But for Pluto, 192 Kelvin is balmy. So taking these 4 end-member models, I'm then going to simulate the initial formation of Sputnik Planitia and form the impact basin. So here what I'm looking at is a zoomed in picture of just what the basin looks like in 2D. And I'm plotting temperature here so that all that red is the warm interior of the basin, and all that yellow and blue is the exterior of the basin. Now, the impact effectively excavates a basin that then collapses under its own weight to then stabilize, which is a process that takes about 3 to 4 hours of real time. But then what happens after that is the basin has to then cool and stabilize into what we now see today. So what I do is I simulate the impact in an impact model, and then I take that out of the impact model, and then I cool and relax it in a different kind of model, which is a process that takes between 40 to 175 million years of geologic time, but fortunately not model time. And to determine whether I've actually made Sputnik Planitia, I look at the topography that we know we have, as well as the gravity signature that the basin should have. Because again, we're pretty sure that it's a mass positive, so it needs to have more mass there than if it was just an impact basin. So on the left, this is the basin topography. We know its average radius, though obviously it's a little bit elliptical, and we can estimate its total depth, which means we're pretty sure it shouldn't be more than 10 kilometers deep at most. And then from there, we're pretty sure it should be either in terms of its gravity, it should have a close to 0 gravity anomaly, because then once that nitrogen ice sits on top of it, it should go positive. And I'm going to show a zoomed in version of the previous impact simulations, looking just at what happens when the basin itself forms. And this is, again, for one of our best fit cases. So here we have a thick ocean and a thin ice shell, and that ice shell is also relatively warm. And on the left, what I'm showing is temperature. with red being hot. And then on the right, what I'm showing is material. So ice is in white, the ocean is in light blue, and the core is in dark blue. And that's the massive impactor. So first thing that happens is we form a huge basin. That basin then collapses under its own weight, and it forms this massive column in the center that we call the central uplift. The central uplift takes a while to collapse. And now that it's collapsed, the ice shell effectively disaggregates for a little bit, leaving the ocean exposed to space. Don't worry about that because the ice shell does eventually flow back into the center of the basin and recoalesce to form thinned ice in the center of the basin and thickened ice outside of it. So there's thinned ice in the basin interior, and that arrow is pointing to an estimate of where we think the basin rim is. That's that thickened zone of ice. And this configuration that I'm showing here is important because, as I mentioned at the start of this talk, if Sputnik Planitia is a positive mass anomaly, then we have to have thinned ice in the basin interior to have that ocean rush in and contribute the extra mass. So we're pretty sure that this configuration that I've established here is a good starting point for Pluto to have a positive mass anomaly later on. But again, this is only what happens after the first 3 to 4 hours after impact, and there's tens of millions of years to consider. So this is, I'm going to show you what happens after I think 40 to 70 million years after impact. And what I'm showing you here is how the basin cools over time. Basically, the first thing that happens is the basin forms like a thin lid in the interior of strong ice. And as everything cools over time, the growth of the purple would be the growth of colder ice. That cold ice then expands inward from the side and downwards from the top to form this stable lid that keeps the basin together. So the basin starts out with thinned ice in the interior and thickened ice in the exterior, and then it remains stable over geologic time. The key point here is that building a Sputnik Planitia-like basin, what we found is we need either a thin ice shell, or if the ice shell is relatively thick, we need this complex balance of ice shell thermal structure and viscosity, because what I've shown you here is a relatively thin ice shell, which is why the ice shell remains stable over time. If the ice shell is relatively thick, the ice gets so warm at the base that it steadily starts to flow inwards, erasing the structure and destabilizing the entire basin. So what we found is either the ice shell has to be relatively thin, which means the ocean needs to be relatively thick, or we need a complex balance to have a thicker ice shell that's warm but strong enough not to flow, which is a little bit more difficult to get. Another way to summarize this would be we favor Pluto having a thin ice shell and a thick ocean at the time that Sputnik Planitia formed because it produces a more realistic basin more easily. So there's 3 things that I'd like you to take away from this discussion of Sputnik Planitia. First, that antipodal focusing from Sputnik Planitia suggests that Pluto has both a hydrated core and a thick ocean, which makes it potentially habitable. Second, Pluto's formation and evolution are consistent with the presence of both a thick ocean and a thin ice shell, and that could favor the formation of a positive mass anomaly later on once nitrogen ice starts to collect in the basin. What this means is Sputnik Planitia's short-term evolution, that is what we saw in the first 1,000 seconds, are consistent with what we're finding in terms of its evolution over geologic time. Both suggest that Pluto has to have a thick ocean and a thin ice shell, which combined with a hydrated core means potentially a very active history. If we combine these 2 things, Pluto may have had a much more active geologic history than anybody previously anticipated. And that's a change in how we think about Pluto as existing over the lifespan of the solar system. And it's something to think about going forward as we apply this to other large Kuiper Belt objects, because Pluto isn't the only large Kuiper Belt object out there. There's at least 7 other large Kuiper Belt objects out there similar in size to Pluto that could have just as complex geologic histories. And I did want to mention a few other things that are of interest, which is the other thing to think about when we're thinking about this is the initial formation of both Pluto and its moon Charon. I wanted to allude to this because I think it's quite fun. So this is Pluto and its moon Charon as viewed from New Horizons. And we don't fully know how Pluto got this moon in the first place, but we think that in addition to the impact which formed Pluto's heart, which is at the center of Pluto here, that there was initially an even bigger impact much earlier in Pluto's history that allowed Pluto to capture its moon. So I've been doing some new and improved simulations to try to understand how Pluto initially got its moon in the first place, because we don't fully understand that process. And if any of you have heard anything about the formation of the Earth's moon, we think it was relatively similar. So I'm going to show you a video of what one of those simulations looks like. And Pluto is here in the center of this image, and its ice shell is in yellow, and its core is in blue. Charon is going to come in from the top right, and Charon's ice shell is going to be green, and its core is going to be purple. And we'll observe what that looks like over time. So Charon hits Pluto, and both bodies become briefly bound together before eventually separating into a stable orbital system. And there's several things to notice here, which might be interesting when we think about then how eventually Sputnik Planitia forms into a planet like Pluto, which in the center of this image has obtained some mass from Charon. These two bodies experience global deformation when they collide. And as part of that, Charon loses not just some of its ice shell to Pluto, but also some of its core, which then Pluto then has to re-equilibrate, potentially before or during the second collision in which something then hits Pluto to form Sputnik Planitia. So there's a lot we don't understand about this period in Pluto's history. I almost played that video 3 times. So the first thing that happens is that Pluto and Charon get stuck together, and then they co-rotate as a single body, similar to contact binaries, which are found at a much smaller scale in the Kuiper belt and the asteroid belt, but this would be quite a big one. But fortunately, they do eventually start to separate. That is all I wanted to share with you all tonight, but I'm happy to take any questions about any of the things that I've discussed. And if you have further questions for me after this, feel free to contact me at the email below. So thank you all.
Okay. Thank you so much, Dr. Denton. I will look to see if there's questions in the chat. And I don't at this point have questions in the chat. We have from David Levy a statement that was, and there came out stars in the heavens like the Arizona star of heaven, he fell upon me. And that's from the Epic of Gilgamesh from the 18th century BC. So thank you, David, for that. Do we have people who have questions who have not voiced them yet? Do you want to let us know if you have questions? And Terry, you can help me monitor to see.
Yeah, I don't see any. Oh, here's some coming in.
Okay. From Doug Summers, we have, whoops, I missed that one. The Doug Summers one went away. So let me click my machine here and see if I can find it. Okay, so Doug Summers says, what chemical compound is the reddish material on the surface?
The reddish material on the surface is another one of the kind of thin veneers that I mentioned. It's just it's one of the more complicated ones. So the red stuff, which you can kind of see at the absolute bottom of this image, so right here is some of that red stuff. Those are what's called tholins. And tholins are kind of complicated, which is why I didn't touch on it before. But basically, it's if you know any organic chemistry, that will help. But basically tholins are kind of a sticky residue of a combination of organic compounds. So it's not just methane, but also oh, what is C2H6 called? Ooh, anyway, it's a series of organic based polymers that then get stuck on Pluto's surface. So it's all carbon based material. But again, it's not very thick. It's a thin layer that forms on the surface. And the reason it forms on the surface is in part because of interactions with Pluto's atmosphere. So Pluto does have an atmosphere. It's relatively thin and it's getting thinner all the time because Pluto is currently moving away from the sun. But Pluto's atmosphere is largely nitrogen, but the tholins are thought to originate from interactions between Pluto's surface and its atmosphere. I hope that answers your question.
Wonderful. Thank you. I missed a question before that from Jeff, which is the hypothesis that Charon collided with Pluto to cause Sputnik planitia?
No, that's a good question though. What's so funny is we think that two separate collisions happened, which is a little bit difficult to explain because it's a little convenient, but we don't actually have a better option. We think that the first collision happened very early on in the solar system, potentially before Pluto was even in the Kuiper Belt, because we think the formation of the Kuiper Belt was a chaotic period driven by the migration of the outer planets, but mostly Jupiter because it's the biggest, which then scattered the Kuiper Belt outwards to its current location. But potentially the collision that formed Pluto and Charon as a two-body system could have occurred during that time. We're not entirely sure, but whenever it happened, it was very, very early on. And then sometime after that, the collision happened that formed Sputnik planitia. The reason we're pretty sure they're not the same thing is because Sputnik planitia is very old, but it's not the oldest thing on Pluto's surface. There's a massive ridge trough system that kind of splits the planet in half that runs from north to south that Sputnik planitia then overprints. And so we're pretty sure that the Charon forming collision formed Pluto and Charon, and then Pluto then started to build up a geologic history, formed this massive north-south trough system. We don't know how that formed actually. And then something hit it, and we formed Sputnik planitia as we know it today. But it's actually pretty hard to get something to hit each other twice in the Kuiper Belt. So why did it happen twice? We don't know yet.
Thank you. Ross says that was an excellent example of the use of modeling to get clues about the geology of Pluto.
Thank you.
And Gary says, I'm curious what resources beyond New Horizons were employed in Dr. Denton's research.
Thank you for asking. Well, a lot of New Horizons was used, true. We based most of our geologic interpretation off of New Horizons, but some of the resources that I used are based off of the formation of other impact basins elsewhere in the solar system, which we've been able to study in a lot more detail, which is why I showed you those images of impact basins on the moon and Mercury. But actually, one of the places that I use a lot as kind of a proxy for Pluto is the moons of Saturn, because if you look at the moons of Saturn, one of those is Mimas, the moon that looks like the Death Star. All of them have these massive impact basins like Sputnik planitia on Pluto. So I use the more robust data that we have for some of the Saturnian moons to try to understand how big Sputnik planitia should be and use that to guide some of my modeling. So I'm not doing additional observing of Pluto with telescopes or anything because Pluto is so small that even with JWST and the improvements that we've made in terms of observing smaller bodies, there's not a lot to be gained right now from observing Pluto.
Thank you. Bernie says, how did you estimate the incoming velocity of Charon prior to their collision?
There are people who make it their life's work to estimate how fast things are traveling around the solar system. So there's basically an inferred average impactor speed of the Kuiper Belt, which is the average speed that things are traveling before they hit each other. And that speed varies throughout the solar system. So the average impactor speed of something hitting Jupiter's moon Europa, for example, is a lot faster. It's around 20 kilometers per second. And the reason for that is twofold. But the primary reason is because Jupiter is so much more massive that it speeds up any incoming projectile, which if you think about what's happening at Jupiter, most of the things that are hitting Europa should be either asteroids or comets that then get focused by Jupiter's gravitational pull. And instead of hitting Jupiter, sometimes they'll hit Europa. In the outer solar system, Pluto is a lot smaller, it's less massive, and it's not a satellite orbiting a giant planet. So the only gravitational pull it has is its own. So everything that hits Pluto is going to be traveling a lot slower. And 2 kilometers per second might seem very fast because we are human people. But in terms of solar system velocities, that's relatively slow and even gentle.
Oh, thanks for that perspective. Okay, another question that we have is what might be the temperature of Pluto's ocean?
Ooh, cold. It's really cold. Haha, we are not sure. The fact if Pluto has an ocean, that means it has to be a liquid, which kind of constrains things a little bit. The way we think about this is, well, I wouldn't ever recommend doing this in real life at all. But we think, okay, so the warmest Pluto's ocean can possibly be is probably close to the melting point. It's highly unlikely that Pluto's ocean is warmer than 273 Kelvin or 0 degrees Celsius. So it's likely very, very cold. Why is it not going to be warmer than that? Because it's very difficult to make Pluto warmer than that. Why? Because Pluto doesn't have a lot of heat sources. Pluto is heated from the inside out by the radioactive decay of isotopes in the core, which does warm up the planet somewhat, but that's not very much. The reason that oceans on other bodies are more possible is because most ocean worlds are like Europa around Jupiter or Enceladus around Saturn. They're heated by the tidal pull of the giant planet that they orbit. So it's a very different situation. In the Kuiper Belt, where Pluto is, the ocean's probably really cold. One way you could have a liquid ocean and have it be colder than 273, so have a liquid ocean that's, below zero, is to stack it up with some ammonia or some antifreeze, which it could have a few weight percent ammonia in it, probably not more than a few weight percent. Nobody's really sure how to reconcile the fact that you need to have a liquid ocean with the fact that we don't have a good way to keep it warm right now. There have been many things suggested. One includes forming a potential insulatory layer of what we call methane clathrates in between the ice shell and the ocean. This would be very convenient because they're a very good insulator. You find methane clathrates in the Earth's seafloor, but you could have them on Pluto, I guess, because you just need water interacting with rock, right? And it's probably doing that. But if you didn't like that example, yeah, we can't prove that. So that was a long answer to your question because we don't really know how cold the ocean is.
Okay, thank you. Another question from Jeff. Did the collision with Charon cause an antipode?
Probably, yeah. The Pluto-Charon forming collision was probably quite traumatic, right? And it was global in nature. But we think it was so traumatic. Pluto and Charon experienced global deformation. What I mean when I say global deformation is literally Charon left a several kilometer thick layer of ice from Charon onto Pluto. So there may have been some form of antipodal deformation occurring, but it was probably washed out by the fact that Pluto is literally getting resurfaced. It's getting a new surface in the process of this collision because material is being transferred between Pluto and Charon as they collide and then separate. So yes, but there was a lot going on. We don't fully understand this process. Which probably also happened in the Earth-Moon system, but because Pluto and Charon are made of rock and ice instead of rock and metal, it's very different.
Okay, a question from Pete is, if you could safely alight onto the surface of Pluto tomorrow, where would you want to go? And what would you do the first few days or weeks there?
That's such a cool question. I would do that tomorrow. I would do it. So thank you for asking. I would love to try to map the rim of Sputnik Planitia. So I would try to land as close to the rim as I could. So in this image, this feature here is the rim of Sputnik Planitia, and it's really old and super degraded, and it's been incised by subsequent glaciation as nitrogen ice kind of flows into the basin center. I would love to try to climb through the mountains that make up the rim and try to map them in more detail, which would allow me to get better information about how old the basin might be. Because the nitrogen ice in the center of the basin is so thick, I wouldn't be able to drill through it myself because it's at least 3 kilometers deep. That's not happening. So I'm not going to be able to learn much from that, but I can learn a lot from the basin rim. So I would start there and try to work my way around.
Great. And the last comment I have is awesome. Thank you. So that's all the questions that I have. Now, Terry, do you have another question somewhere?
Yes, I've got several questions and comments from Facebook.
Okay.
Oh, Thomas says, I studied planetary science under Eric Osfog at UCSC back in 2004, almost forever ago. I love planetary modeling and impactor simulations. This talk brings back fond memories. Uh, and then from Ed, how similar to Pluto do we think the other large Kuiper Belt objects are?
Uh, Kind of hard to say given that we know a lot less about them. Most of what we know about them is their size and their mass. What I can tell you is that 8 out of 10 of the largest Kuiper Belt objects have a large mass fraction satellite, meaning 8 out of 10 of the largest Kuiper Belt objects have something similar to the Pluto-Charon system. So Pluto and Charon are a binary system. They're not complete. The Charon doesn't rotate around Pluto. Pluto and Charon rotate around a point that's slightly outside of Pluto because Charon is so massive. Many of these other large Kuiper Belt objects are similar, which raises an interesting question of how did all of these other guys form? There's Eris, which was the body that was initially discovered that made Pluto no longer be a planet, and its moon Dysnomia. There's Haumea and its 2 moons, Hiaka and Namaka. There's Makemake and its moon, which doesn't have a name. They just call it MK1. And Orcus and Vanth, which Orcus and Vanth are really cool. Nobody knows about Orcus and Vanth. But they're basically a 40% scale model of Pluto and Charon. They have the same mass ratio. They're just 40% the size. So if you think from a perspective of how are all these bodies formed, they may have formed through a similar process, through Charon hitting Pluto. Potentially you had collisions like that happening all over the Kuiper Belt to form these large Kuiper Belt objects with large mass fraction satellites. What we don't know is much about their interiors, including, again, whether or not they would have oceans. We know that Eris is more massive than Pluto, which combined with telescopic information indicates that it does have an icy shell, but it just has a much bigger rocky core relative to Pluto. That doesn't preclude an ocean, but we don't know much more than that. Eris could have had even more ice that got stripped off by impacts over time. But they all likely have a similar structure. They likely all have rock at depth and then ice at the surface. And then they may have all experienced similar giant impacts, but there's a lot more to try to figure out.
Okay, thanks. And then Thomas follows up one with the fond memories from 2004. He says, what software codes are common for modeling these days?
Fun question. Well, for impact modeling, I use a code that's called ISAIL. It stands for alternating Lagrangian Eulerian, which is the framework that we use to do the modeling. It's basically switching between a Lagrangian framework for modeling and an Eulerian framework for modeling. I can explain this later if people want, but basically it's a way to track the movement of material that's traveling at really rapid speeds and deforming really rapidly. And there are other codes that do this. Most of them are not open source. It is quite difficult to get an impact modeling code that is open source. Why? Because impacts are very similar to explosions. So most codes tend to be national labs type codes and difficult to access. This is not always true. There's a whole other series of codes that are called SPH, which stands for smooth particle hydrodynamics. And those are the collision between Pluto and Charon that I showed you was an SPH code where everything is simulated as particles. And in those cases, smooth particle hydrodynamics codes are typically used to simulate galaxies colliding with each other. And what we've done there is shrunk it down so that we can make planets collide instead. That has its pluses and minuses, but SPH codes tend to be open source. So for that, I use an SPH code, which you could find on GitHub if you wanted. And then in terms of the long-term geologic evolution, you can't use an impact code for that because impact codes are designed to look at what's happening on like the microsecond scale. And that doesn't scale well to geologic time, which takes place over tens to hundreds of millions of years. So for that, I actually use what are called finite element codes, which engineers use all the time. I'll take something like Abacus or COMSOL, things where engineers build car engines. You can also use them to build planets. They just don't tell you can do that. So that's what I use.
That's really interesting. Okay, so that was the last of the Facebook questions. Thanks.
Okay.
Cool.
Well, thank you, Dr. Denton. This has been just a fascinating presentation, and we appreciate your coming so much. And we hope that you will come back again later and let us know some subsequent developments from tonight,
So
so that we
what-
can find out more about, how your research evolves.
Thank
There's
you.
a question, May.
Uh-huh.
Yeah. So Steve says, do you consider Pluto a planet?
Wow, what a question to end on. Thank you, Steve. I've called it a planet in this talk quite a lot, haven't I? Well, I consider it to be a planet because I consider anything that's interesting enough to have its own geology is a planet to me. That's a very like unconventional definition, I'll admit. I miss the days when Pluto was a planet. So emotionally, yeah, it's a planet to me. But realistically, it's such an interesting class of object. And there came a point where we discovered so many bodies like Pluto in the Kuiper Belt and Ceres in the asteroid belt that I am okay with Pluto being the first of its kind of this new class of bodies that we now call dwarf planets. They're all so interesting in their own right. So yeah, Pluto is a planet to me, but I won't get super mad if you don't think it's a planet. That's okay too.
Thank you very much, and we certainly hope to see you here again in the future. Thank you,
Thank you so
Dr.
much for
Denton.
having me.
I also wanted to announce, Dr. Eric Kokoschka wanted me to make sure that you knew that he's not available to be here tonight to do his planet presentation for the month, but he wanted you to know that it has been posted on the TAAA website if any of you is interested in following the planets for the month. So I'd like to say goodbye to Facebook now, and thank you so much for our Facebook visitors from coming. We're here every month, usually the first Friday of the month, and we appreciate your coming to visit us. And the presentation will be posted for the future. So thank you.